In the previous activity, we talked about the sampling distribution for the difference of two sample proportions. We also talked about constructing a confidence interval to estimate the difference of two proportions. In this video, we're going to talk about significance tests for the difference of two proportions. And just like any other significance test, we have a one-sided alternative or a two-sided alternative. And you're going to see a lot of similarities here to a significance test for a single proportion. You're also going to see a lot of similarities to a confidence interval for the difference of two proportions. So let's get started with our example. Our example is based on a study done by the National Sleep Foundation, and our information is the following: that they did a survey, and of the 995 respondents, 37% of adults reported that they snored at least a couple nights a week during the past year. Would you expect that percentage to be the same for all age groups? When split into two age categories, 26% of the 184 people under 50 snored, compared with 39% of the 811 in the over 50 age group. Is this difference of 13% real, or simply due to natural variation in the samples? So we're going to see what the evidence tells us by way of a hypothesis test. And so our hypotheses are going to look something like the following. H naught, the proportion that snore that are over 50 is equal to the proportion that snore over 50 is equal to the proportion that snore under 50. Now, typically what we do is we write this as a difference because we want to set that difference equal to something, and in this case that difference would be equal to 0. In other words, there's no difference in the proportion of people that snore that are over 50 versus under 50. So proportion over 50 minus the proportion under 50 is equal to 0. Our alternative, we want to know if there's a difference, not if one is greater than the other. So the proportion over 50 is equal to the proportion under 50, or not equal to the proportion under 50, which translates to the proportion over 50 minus the proportion under 50 is not equal to 0. And we could have taken this difference either way, over 50 minus under 50 like we did, or vice versa. In doing this hypothesis test, we are going to use a standard error that is similar to the one that we used for the confidence interval for the difference of two proportions, with one minor change to it. And that minor change is going to be based on the assumption that the null hypothesis is true. In other words, that the two proportions are equal to each other. And before we get to that, let's do some calculations here and figure out what we have. How many snorers are in the under 50 age group? Well, based on the data, we have the following. We know that 26% of the 184 people, or approximately, we need to round to a whole number here, 48 in the under 50 age group snored, and 39% of the 811 people in the over 50 age group, which is approximately 316 people, snored in that age group. Since we are assuming that the null hypothesis is true, it's always our starting point, we are going to find a new measure. We call this p-hat combined, and it basically says, let's take the number of people in one group, approximately 48, plus the number of people in the other group, approximately 316, that snore, and divide it by the total number of people in the study, 184 and 811, and this turns out to be 364 out of 995, which is approximately 0.3658. So as I mentioned a moment ago, we are going to calculate the standard error a little bit differently for a hypothesis test for the difference of two proportions than the formula we used for the confidence interval for the difference of two proportions. And what we're going to do is we're going to use this p hat combined in place of p1 hat and p2 hat. And to calculate p hat combined, you basically add up the number of successes in the two populations and divide by the total of the two sample sizes. So when it comes to calculating the test statistic, it is the same format as always. It's your statistic, in this case, which is the difference of the two sample proportions, minus the hypothesized difference, which in most cases is 0, divided by the standard error, which you will see uses p hat combined in place of p1 hat and p2 hat. As far as the conditions for inference are concerned, for a hypothesis test for the difference of two proportions, they're the same as the conditions for the confidence interval. So let's take a look at verifying the conditions. So I'm going to label the under 50 group and the over 50 group, and we're going to take a look at n times p hat, so 0.26 times 184 is equal to 40, approximately equal to 48, and the complement of that 0.74 times 184 is approximately equal to 136. So both of those are at least 10, so we meet that condition of approximate normality for the sampling distribution for that population, or for samples from that population. The over 50 age group 0.39 times 811 is approximately 316, and the complement of that 0.61 times 811 is approximately equal to 495, and again, both of those are greater than 10, which tells us that when we combine the two proportions, or combinations of the two sample proportions, we create a new sampling distribution, which is also approximately normal. The data is stated to be from a simple random sample, and because the data is from a random sample, it seems reasonable that the results of the survey are independent between the two age groups, and within them, I think it's reasonable to assume that we've met the 10% condition. So both samples less than or equal to 10% of the corresponding populations and both samples, well, we'll just say samples reasonably independent of each other. And remember, this last condition is the added condition when we're talking about inference for differences. So our calculation is going to go something like this. Z is equal to 0.39 minus 0.26 minus the hypothesized difference of 0 over the square root of 0.36 times 0.64, I'm rounding here, for p hat combined, over 811 plus 0.36 times 0.64 over the second sample size of 184. And if you verify that, you get a z value of 3.27. And that corresponds to a p-value of approximately 0.001. So instead of writing out the interpretation of this p-value, we're going to say, assuming alpha is equal to 0.01 even, which is very small, the p-value is less than alpha, therefore we reject H0. Therefore we have convincing evidence of a difference in the proportions of those that snore in the two age groups. So the last thing I'd like to do is show you how to do this calculation on your calculator. Obviously you need to state the null and the alternative and check all the conditions, define your parameter, show your calculations, calculate a p-value, and interpret the conclusion in context. But I would highly recommend that you know how to do this on your calculator. So stat, go over to tests, and this is a 2-prop z-test, which is not shown up here, so we're going to go down a little bit further, and we have a 2-prop z-test. Where is the 2-prop z-test? Oh, it is showing up there, number 6. So we're going to select number 6. x1, the number of successes. Remember, these have to be whole numbers, so we rounded off to the nearest whole number, 48 out of a total of 184, I believe it was. For the second group, it was a total of 316 out of a total of 811. And our alternative hypothesis was not equal to, and we are going to actually calculate this. All right. The nice thing about this is not only does it calculate the z value for you, which, by the way, you'll notice I got a negative 3.27 here, and that actually doesn't matter because switching them around is going to get you the same p-value. So there's our p-value of 0.001, p1 hat of 0.26, and p2 hat of about 0.39. And you'll notice the p hat with no subscript c is actually p hat combined, so it calculates that for you. So that's how you do the corresponding hypothesis test on the graphing calculator. So what I'd like to finish up with is a summary of the conditions that you need to check when you're doing a hypothesis test for the difference of two proportions. So you need to check randomness for both samples. You need to check normality for both samples by taking n times p hat and n times 1 minus p hat, and they all have to be at least 10. You have to check independence within the samples, and you're going to do that by the 10% condition, but you're also going to check independence between the two samples. So the two random samples from the two populations must be independent. And just think about the context there, how the samples were selected. This is an additional condition for independence and is not based on the independence within the sample. Within the sample is the 10% condition. So if you'd like to, pause the video and work through problem number 2. And then when you're done, you can unpause the video and I will take a moment to go through it. So this is a study about the parental influence on a teenager's decision to smoke. And either the parents were lenient or they disapproved of their kids smoking, and then the proportion that ended up smoking. Turns out that this is a prospective study, meaning it follows them into the future. And out of the proportion that disapproved, about 19% of them ended up smoking, became established smokers. Out of the proportion of parents that were lenient, about 26% of those kids ended up becoming smokers. The combined proportion, add up the two numbers of successes and divide by the total of the two sample sizes, turns out to be about 20%. Our null and our alternative hypotheses look like this. I took the proportion that were lenient minus the proportion that were disapproved equals 0. You could have done it either way. The only difference is when you do the calculation, you would get the opposite sign for the test statistic. It did not mention that there was random sampling, so that's a concern. All the n times p hats and n times 1 minus p hats are at least 10, so we can assume that the sampling distribution of the differences of the sample proportions is approximately normal. As far as independence is concerned, I think it's reasonable that we meet the 10% condition. The samples were less than 10% of the corresponding populations. However, it's hard to say if the responses were independent because we don't know how the data was collected. When you get around to calculating the test statistic, remember, take the difference of the two sample proportions minus the hypothesized difference, which is 0 in this case, divide by the standard error, which is calculated using p hat combined. You get a z-value of either positive 1.17 or negative 1.17. In either case, you get a p-value of 0.24, which under any circumstances is not strong enough evidence to suggest that there was a difference in the proportion of students who ended up smoking based on their parents' attitudes towards it. Now, I'm going to go on and talk about the corresponding confidence interval here. So the confidence interval, again, the difference of the two sample proportions. We're constructing a 95% confidence interval, so we have the critical value of 1.96. And notice, for the standard error, for the confidence interval, we do not use p hat combined because we are not assuming the null hypothesis is true, which was that the two proportions were equal. So you'll notice that our confidence interval contains 0, which basically says that, or confirms that the difference could be 0, and our standard interpretation of this confidence interval. We're 95% confident that the difference in the proportions of the smokers from parents with the different attitudes towards smoking lies in the interval from negative 0.06 to positive 0.22, which includes 0. This suggests that there is no statistically significant difference in the two proportions at the 5% level of significance.